All right, let's go ahead and get started. So this is going to be the last lecture on dynamic programming. We'll have another lab tomorrow where we go through a few more interesting problems. But there, and the examples that I'm going to be doing today are by design a bit more complicated than the examples that we've seen before. These are not necessarily things that I want you to be able to absorb in complete detail, but there are a few places, a few features of the dynamic programming algorithms that I'm going to show you that do occasionally show up in other problems, for example, problems that might show up in lab tomorrow or in the homework, and are worth thinking about. So if the fine details of the examples I'm showing you don't make it in, I will try at least to wave a flag saying this part is important, pay attention to this, okay? But the examples I've chosen to talk about are related to regular expressions and context-free grammars, in part because this is one of the things that the course is about, and because some of these things that I'm going to show you are really, in fact, the best we know how to do for the problems at hand. Before I get into the new examples, though, I do want to go back and say a bit more about the last example that we saw on Tuesday, just computing edit distance. So if you can remember, the problem is I'm given two strings, and I want to transform one into the other, right? Another way of thinking about this is I want to produce this sort of two-dimensional thing out of two strings, in this case, algorithm and altruistic, where the way I fill in each column tells me something about how I would transform the string at the top row into the string in the bottom row. So in this particular case, what this box represents is the statement, I can transform algorithm into altruistic by deleting the G, changing the O into a T, inserting a U, inserting an S, changing the H to an I, and changing an M to a C. So altogether, I can do 6 editing operations to change the first string into the second. There's 2 insertions, 1 deletion, and 3 replacements. The columns where the character above and the character below are the same don't count as operations. Those are sort of free. The columns where there are two symbols that are different, that's a replacement. This is a deletion. That's an insertion. And the problem is to figure out the set of editing operations that's as small as possible in this representation to transform the first given string into the second. Okay, so I'm given these two strings. I'll call them A and B. And we could define a recursive function called edit. In class, we did it for suffixes. In the lecture notes, I do it for prefixes. They're both right. The prefixes formulation is a little slightly cleaner, but there's no one is right and the other is wrong. So edit ij denotes the number of operations that I need to transform the first I characters of string A into the first j characters of string B. And this function satisfies a nice recurrence. If either of the two strings, either of the two prefixes is empty, the answer is the length of the other prefix. So if I need to change the empty string into a string of length j, I need j insertions. If I want to change a string of length I into the empty string, I need I deletions. If I want to change the empty string into itself, I do 0 everythings. And both of the two base cases correctly give me 0. Done. And then the recursive case, if both of the prefixes are not empty, I have 3 possibilities for what I can do. I can decide I'm going to delete the first character of A, the last character in the prefix of A, in which case I add 1 to pay for that deletion, and then I recursively look at a slightly shorter prefix of A and the same prefix of B. Or I can decide that the last thing I'm going to do is insert the last character of B, in which case I add 1 to pay for that insertion, and then I recursively try to transform the whole prefix of A into a slightly shorter prefix of B. And the last possibility is I do a replacement, and I recurse on slightly shorter prefixes of both strings, and then the cost of that replacement is either 0 or 1, depending on whether those two characters are equal. So that expression in brackets evaluates to 1 if the two characters are different. I had to pay for the replacement, and 0 if I didn't. Okay, so that gave me a recurrence. By recurrence, the function has 2 parameters. They're both integers between about 1 and about n. So I can memoize that function into a 2-dimensional array. Here's what it is. In this case, every element in the array depends on the elements immediately above, immediately to the left, and immediately above and left. And so a standard for I equals 1 to n, for j equals 1 to m will fill it in. So I can, in this case, I can fill in the array just using a standard pair of nested for loops in the usual order that you would do if you weren't thinking about it. Is there a question?
The quick question is, why are you calling it on I-1 instead of I-1?
So the formulation that's in the notes is slightly different than the formulation in class. In class, we were recursing on suffixes by trying to figure out the first editing operation. Here, we're recursing on prefixes by trying to decide on the last editing operation. And the only reason for wanting to do that is to avoid having to do index arithmetic in the base cases.
So you're going from reverse?
I'm going from the right. I'm chewing away from the ends of the strings instead of from the beginning. But this is an arbitrary choice. I just made it this way because, as I said, it makes the notation epsilon cleaner. Okay. Okay. And now if I actually fill in all the values, those numbers are what you get for that pair of strings, algorithm and altruistic. Ignore for the moment the arrows, but let me just focus on a particular value here. Let's suppose I'm trying to turn algorit into altruist. Okay, in other words, I'm trying to figure out what goes in this spot in the table. So according to the recurrence, that number is the minimum of three things. The number immediately above it plus 1, the number immediately to the left plus 1, and the number above and to the left plus 0, because the two characters are equal. And so what the algorithm will do when it gets to this point in the array is it will say, well, which is smaller, 5 or 6 or 4? And it'll pick 4 because that's the smallest number, and it'll write the 4 there. Okay. Now, the arrows that I've drawn in this picture tell you how I got each of the values in the table. Right? So whenever there's a downward arrow, it's because the right choice to get this 9 was 8 plus 1 as opposed to 9 plus 1 or 10 plus 1. Right? Whenever I have a right arrow, it's because the choice, why do I have a 6 here? Because, well, that was the smallest of 5 plus 1, 6 plus 1, and 7 plus 1. And in some cases, there are ties. So if I look at this 2, for example, here in the middle, it could either be the one to the left plus 1 or the one above to the left plus 1, and I don't care which one. Okay. Now, what do these arrows, first of all, what do the arrows tell me? It sort of tells me if I'm in this situation, the arrow tells me what the last editing operation should be, as opposed to just telling me what the cost of the optimal, what the edit distance is. All right? So I have three choices, from above, from the left, or from above and left. And the arrow tells me which of those three I should do. And what that means is, if I'm going down into this, to get here, I should do a deletion. To get here, I should do an insertion. And the diagonal arrow means I should do a replacement. And so now if I want to figure out what the actual optimal sequence of editing operations is, all I have to do is start down here at the bottom with the number 6. That's the actual edit distance I care about. And walk backwards along arrows until I get back to the beginning. Right? And now I can read off. You should do replace, replace, delete, replace, replace, insert, replace, insert, replace, replace, replace. Okay. I don't think this is exactly the same as, well, in fact, yes, this is exactly the same as what I did here. Right? That path through the table describes that sequence of editing operations. There's more than one path through the table that follows the arrows. That means there's more than one optimal way to transform one string into the other. That's fine. Right? So if you wanted an algorithm that says, give me the optimal, the smallest set of editing operations that goes from one string to the other, and in fact there's more than one correct answer, then you should just feel free to return whichever one you want. Right? There are multiple ways of getting from one string to the other here in 6 steps. Okay? Any one of them is fine. Moreover, these arrows are not actually something I need to compute. Right? I can actually just look at the numbers, and just by looking at the numbers, figure out what arrow is pointing into any particular value, right? What arrow is pointing into the 6? I just compare the 3 neighbors, 5, 6, and 7 nearby, and say 5 is the smallest, the arrow must be coming from the left. So the punchline of all this is once you have the table of values, you can reconstruct the sequence of editing operations that you're actually looking for, right? This is the reason why when I say describe an algorithm to compute the optimal sequence of editing operations, it's enough just to tell me how many. When I say find the longest increasing subsequence, what I really mean is just find the length of the longest increasing subsequence. Because once you have that memoization table, you can reconstruct the actual sequence afterwards in a post-processing step. Right? So whenever I say construct X that's optimal, what I really mean is compute the cost of the best X if you were to build it. Because the step from figuring out the optimal cost to figuring out the actual optimal structure is often just to sort of walk backwards through the array. Essentially what you're doing when you're reconstructing the sequence of editing operations is you're running the backtracking algorithm. Except instead of recursively trying an insertion, recursively trying a deletion, and recursively trying a replacement, you look at the 3 scores, and on the basis of those 3 scores, you know which of those 3 is the right option to try recursively. So instead of this weird exponentially branching thing, you just follow a path straight back to the base cases. Okay? Questions? Yeah? Oh, the bold arrows are just the diagonals that don't cost anything, because they correspond to pairs that are the same. Which, yeah, so for example, when I'm at this 3, I could have gone up and left instead of straight up. Why did I do one or the other? I felt like it. Why not? What? I'm sorry? The bold arrows are the ones that correspond to pairs of characters that match. In the recurrence, this is when the bold arrows are when this expression is equal to 0. Okay? All right. So there's one other thing that I want to point out here. Notice that if you look carefully at this table, you'll notice that every possible place in the table where 2 characters are equal, the right choice is to do a free replacement. All right? In other words, even though in this recurrence I say, well, I'm just going to try all 3, in fact, when the last 2 characters are the same, the right thing to do is always the 3rd choice. Okay? And inevitably, when you're developing your own dynamic programming algorithms, you may discover, wait, if they're the same, why would I do anything other than keep them together? It seems stupid to break them apart and do a deletion and later have to do an insertion when I could have just kept them together for free. Be very careful. Don't do that. Don't follow that train of thought until after you've got the entire algorithm written down. First, make the algorithm work. Then you can step back and say, is there anything I can do to make this algorithm faster or simpler, even in practice? And the answer here is yes. Whenever the AI and BJ are the same, the 3rd choice is, in fact, always the right one. But the only reason that I know that is because I've actually written down a proof. Especially when you're in an exam, you don't have time to write down a proof. In fact, I haven't even told you yet how to write down a proof. We'll do that on Tuesday. Right? What you're doing when you're trying to make that little optimization, this is clearly the right choice. This is obviously the right choice. Is you're applying what's called a greedy heuristic. you're saying, I'm not going to recursively try all of the options. I have good reason to believe that this choice is the right one, even though I haven't done any recursion yet. Okay? And there are circumstances when greedy algorithms will work. But in this room, they are rare, and they require proofs. So I want to recommend the following completely serious strategy on exams. If you find yourself starting to write down a greedy algorithm, stop and realize you've just told yourself that the problem can be solved with dynamic programming. Okay? By the end of the month, we'll see, there's some graph algorithms, and there's some dynamic programming algorithms, there's some divide and conquer algorithms, and then maybe there's a greedy algorithm. And I'll just say, here's a problem, solve it. And if your initial intuition is to try to do something greedy, 90% of the time, that means you should use dynamic programming. Right? It's great to have that idea to use the greedy algorithm, not because the greedy algorithm will work out. It won't. But because it tells you what approach will work. Okay? So if you find yourself writing down the word greedy, slap your hand, scratch it out, write the word dynamic programming, and keep going. Okay? All right. Like I said, we'll see the tools to how you would prove something like that next week. But in general, don't try to make these clever optimizations. I mean, ultimately, the dynamic programming algorithm just brute force recursion, except you don't repeat yourself. That's what dynamic programming is. All right. Questions about edit distance? Okay. So, as I said, the problems I want to talk about for the rest of the lecture are a bit more advanced, slightly more complicated as dynamic programming algorithms go. I mean, the recurrences are more complicated. Come on, you can do it. I don't know why this is so hard. But there's some interesting features in here that do show up in some other algorithms. And the particular example is one that is important for 421. It's important if you want to do any sort of AI, natural language processing, text processing, information retrieval. This is the so-called parsing problem. And at a very high level, the problem, the way that I'm going to formalize this, is you're given a string, W, and you're given a grammar. You're given some description of a language, which in this case is going to be a context-free grammar. And then the question is W in the language of G? Okay? So you can think of this as a special case as, is this a syntactically correct Python program? All right? Someone somewhere has written down a specification, a grammar, that accepts a string of Unicode UTF-8 characters if and only if that string represents a syntactically correct Python program. Okay? Now, the language of Python programs is not a regular language because you have various kinds of nesting, parentheses, and so on. But it is a context-free language. It can be described by a context-free grammar. And so this becomes an instance of this problem. Now, actual Python interpreters and compilers don't solve the problem the way I'm going to describe it for two reasons. One, they're written specifically for Python. The grammar is hard-coded into the algorithm. And two, the grammar of Python is not so completely arbitrary. It's actually a very special kind of context-free grammar that allows for faster parsing algorithms. So this is more like a meta-compiler. You give me, on the one hand, the spec for what it means to be a correct program, and on the other hand, a program, and you want to match the two to see if they're actually, see if the program is actually right. Okay, so if you remember what a context-free grammar looks like, this is a nonsense context-free grammar that I just made up. It doesn't represent anything. Well, it represents some language. I just don't know what the language is. So just to remind you what the syntax here is, the capital letters are what are referred to as non-terminals. They represent sets of strings. The arrows pointing from a non-terminal to something else, these are called production rules, right? And so what the first production rule is saying is that the set of strings described by S, a string is in the language of this non-terminal S under four circumstances. One, the string is the string 0. 2, the string is the string 1. 3, I can split the string into a prefix that's in the language of non-terminal A and a suffix that's in the language of non-terminal B. Or 4, I can split the string into a prefix that's in the language of B and the suffix that's in the language of C. All right? So here's one that you might have seen before. This grammar over here on the right, it represents the set of all strings of the form 0 to the n, 1 to the n for some number n. Every string of the form 0 to the n, 1 to the n is either empty when n is 0, or it's a 0 followed by 0 to the k, 1 to the k, followed by 1, where in this case k happens to be n minus 1. Okay. Now, this is what I referred to earlier in the semester as a kind of generative model for the language. I can imagine saying, well, from the beginning, looking at this grammar on the right, start out by saying, well, I know the empty string is in S. And once I know the empty string is in S, that tells me the string 0, 1 is in S. Right, so I can start generating the grammar. And then I can 0, 0, 1, 1, 0, 0, 0, 1, 1, 1, and so on. And likewise, I can generate the set of strings described by the grammar on the left. But it's going to be a little bit more complicated because I have more than one non-terminal. I really have to build up not one language, but 4 different languages. The language of S, the starting non-terminal, that's the grammar. But also A, B, and C are themselves represent languages. Right? So, at the beginning I go, well, S has a 0 and 1, and A has a 1, and I don't know about B, and C has a 0. But once I know A contains the string 1 and C contains the string 0, I know B contains the strings 0, 1, and 1, 0. And A contains the strings 0, 1, 1, 0, 1, 1, 0, 0. I can start building up larger and larger things. Now, if I'm given a new string and is given some And I want to know, is that new string in the language described by the non-terminal s in this grammar? I mean, even if I ignore what the rest of the grammar looks like, I kind of, there's kind of a natural strategy to apply here. Okay? You know, is that string in the language of this non-terminal? Well, there are 4 things for me to check. I don't know which one of them, if any of them, is going to work out, so I'm just going to check all 4. Is that string 0? No. Is that string 1? No. Okay. Is that string of the form AB? Well, I know that there is, you know, there are non-terminals called A and B, but I'm going to imagine that it's somebody else's job. In particular, I'm going to imagine it's the recursion fairy's job to tell me, given any string shorter than this one, whether it belongs to the language of A, whether it belongs to the language of B, and so forth. So if I want to know whether this string matches the rule S goes to AB, then my question is, I need to break off a prefix and pass it to the, you know, the subroutine that matches against A, and I'm going to take the suffix and pass it to the subroutine that matches it against B. And as long as both of those subroutines come back and say yes, then I say, yes, in fact, this string is in S, because I can generate, say, 0011 using A, and the rest of the string using B, and so this matches AB, and S you know, has a rule that says if you're an AB, then you're already in S. Great. There's only one problem with this. There's another thing that I don't know. What do I not know? You know, besides whether to try A, B, or to try B, C, I'm gonna just try them both. But there's something else that I don't know. I'm sorry? Where to break up the string? It could be that I want to pass in 00 to the subroutine for A and everything else to B. It could be that I want to pass in 00110100 to A and 101 to B. I don't know where that split is. So what should I do? Try them all. Right? Not, you know, in other contexts, the answer might be, let's think about this for a while, and maybe we can reason out that we only have to try things after 3 1s and a 0. No. Try them all. Okay? And so I'm kind of starting to get a bit of intuition about how a recursive backtracking algorithm might work. If I want to figure out whether a string is in S, the language, first I check whether the string matches any strings on the right-hand side of a production rule. That's just linear time comparison. That's easy. But for the more complicated production rules, I try all possible ways of breaking up the string and try to match them against all possible right-hand sides of the production rule. And if one of these things that I tried works, I say yes. If they all fail, I say no. Yeah?
By checking for terminals first, do you avoid?
This actually is an excellent question. What keeps me from infinite looping here? I'm going to make the following technical restriction in my grammars, which this grammar actually violates, which is no epsilon productions. Okay? And the reason that I want there to be no epsilon productions is that in that case, if I decide, you know, maybe I'll do something like this. Okay, so here is a parse tree for the string 0, 1, 0, 0, 1, 0 for this original language. Okay. Because there are no epsilon productions, in any parse tree that matches the string, the left subtree is going to be a parse tree for a non-empty prefix, and the right subtree is going to be a parse tree for a non-empty suffix. And so whenever I do the recursion here, looking at the subpatterns A and B, I'm recursing on smaller strings. I'm always throwing something to A and something else to B. I never recurse with the empty string A and everything to B. And so that allows me to avoid this infinite looping problem. Okay, now this is a technical restriction that I'm putting on the grammar, but as it turns out, every grammar can be massaged into a form that satisfies this restriction. You never have any epsilon productions, except possibly the starting symbol just generates the empty string, but that's easy to check. Right? Basically, you can have a bit attached to the grammar that says, oh yes, and the empty string. And except for that, there are no epsilons anywhere in the grammar. Okay? So that avoids the infinite looping problem. There's another technical condition that I need to put on here. Suppose my grammar had a rule that looked like this. And now I want to match, again, some string. Then the question I have to ask is, what are all possible ways of breaking up the input string into 5 pieces and then passing one to A, and the second one to B, and the third one to A, and the fourth one to D, and this is getting horrible and ugly and complicated. I can already tell that this would mean in my inner loop I would have to be checking for all indices I, J, K, and L in the middle of the string. I'm going to get something nasty into the fourth-ish, just because I have to figure out all possible ways of splitting a string into 5 pieces. Right? So I'm also not going to allow this. I'm not going to allow the right side of a production rule to be longer than 2. Okay? So to put all of the restrictions on one page, I'm going to assume that my grammar has something called Chomsky normal form. It means every production has one of 2 forms. Every production rule is either non-terminal goes to 2 non-terminals, not 1, not 3, not 17, but 2, or non-terminal goes to exactly 1 symbol in the actual alphabet. Not 0, not 2, not 17, 1. Okay? And with this restriction, really what this restriction imposes is that the parse tree that you end up with is always going to be a full binary tree with exactly 1 symbol at each leaf. Right? Every internal node will have 2 children, because every non-terminating production, I have 2 non-terminals on the right side, and every leaf will contain exactly 1 symbol. So when I ask, given a string W in this context-free grammar G, is the string in the language? One way that you can interpret what this question is asking is, can you find me a parse tree for this string that is consistent with the production rules of the grammar? And in fact, when you're dealing with programming languages, when you're dealing with natural languages, when you're doing applications of parsing, this is the problem that you actually want to solve. You don't just want to know that this is a syntactically correct Python program. You want to understand the structure of the program. You want to build a data structure that says, oh, this part of the program is an arithmetic expression that's a sum of some stuff in parentheses where this is the product of something and this is an array lookup with this array and this index. Right? That's exactly what this parse tree is. This is the abstract representation of the structure of the program that you're parsing. Or, you know, I want to know, okay, this is a sentence where I have a subject, I have a verb, I have a direct object, and the subject is a noun phrase that has an article and two adjectives and a noun, and the verb has a past participle and an adverb hanging off of it. If you've ever done any sentence diagramming, what you were really doing is parsing. How many of you have ever diagrammed a sentence? I'm curious. Quite a bit more than I thought. Good. That's what sentence diagramming is. Sentence diagramming is parsing. And when you learn to diagram sentences, what you're actually learning is some 19th century English school teacher's idea of a context-free grammar for English. That's what all those rules are that you learned about, you know, agreement and you know, the adverb goes here and the adjective goes there and the past participle relative clauses. So that was a big, giant context-free grammar for English. Linguists hate it. It is total fiction. English does not actually behave that nicely. English is not, in fact, a context-free language. It is a much more interesting structure to it, which means you are not going to be able to apply the algorithm that I'm talking about really to parse English. But you might be able to parse interesting subsets of English, interesting, you know, restricted context English, like 19th century English school teacher English. Okay? But if you talk to anyone who actually does any linguistics, and you say, "Wow, you know, this was the only good part of English class for me is when we were diagramming sentences," they'll just, "Oh God, no," right? Because this is not at all how real language works. Real language, you know, the models that linguists use actually end up building things that look a lot more like trees and a lot less like those branching things. Okay. All right. So now, so my input's going to consist of this grammar in Chomsky normal form and some string. In this case, you know, maybe this isn't the whole string. Maybe there's, you know, more stuff hanging off here that I haven't shown you. Now, my decision, the decision that I have to make is, if I'm trying to match this string to one of my non-terminals, first, which production rule do I apply? And second, where do I break the string? Now, when I decide to break the string somewhere, it's going to be into a prefix and into a suffix. And then I'm going to recursively, you know, look at the suffix, say, and I'm going to have to decide, for this suffix, I'm trying to match it against C, which production rule for C do I apply, and where do I break up the string? And so again, I'm going to break this suffix up into its own prefix and suffix. And then the string in the middle, I'm going to break up into its own prefix and suffix, and so on. What this means is that the string that I'm going to be passing down to my recursive children is always a substring of the string that I started with. It's not necessarily a prefix, and it's not necessarily a suffix. It's just something in the middle. Okay? So the general recursive problem that I actually want to solve might be described as follows. I, J, A. I and J are indices into the string. A is a non-terminal. This is, does the string starting at index I and ending at index J match the language of non-terminal A? right? And now, when I'm faced with this question, either I'm going to be in a base case where the string is just one character long, or I'm going to try to split the string into two smaller strings and pass them to other non-terminals. Okay, so let's try to write that down. Okay. So there are two possibilities here. One is the string is a single character long. Now, remember, every production rule looks like one of these two examples. And there are no epsilons anywhere, and that's it, right? So if the string is one character long, there's no possibility at all that it's going to match this first production rule A to B, C, because B has to match something non-empty, and C has to match something non-empty, and that's too many characters. So if I is equal to j, if the string that I'm passing in is one character long, it has to match a production rule that looks like this. Right? So if I is equal to j, the only possibility is either yes, and there's a production rule that goes from A to WI. Right? If there's a production rule that goes from this non-terminal directly to the ith symbol in the input string, then the answer is yes, I applied that production rule. Okay? False if I equals j and there's no production rule from A to WI. And those are the only two things that can happen when the string has length 1. If the string has length more than 1, then I have two decisions that I need to make. One, which production rule do I apply? Two, how do I break up the string? So I'm going to try all possible production rules, and I'm going to try all possible ways of breaking up the string. And if any of those work, then I'll return yes. If none of them work, I'm going to return no. In other words, I'm going to try this possibility or this possibility or this. I'm going to have an or of several different possibilities. So I'm going to use this notation that I used before. A big V, this is like, you know, sigma is to plus as the big V is to the word or. Okay? Over all production rules starting with this non-terminal A. I'm going to try them all. And then for each production rule, I'm going to try all possible ways of breaking up the string. So I have the string now that starts at index I and ends at index j. I need to figure out where to split it. And to specify that, I'm going to tell you where the left part of the string ends. The last index of the left part of the string. So I'm using this wonderfully mnemonic letter L, also because L is reasonably close to I and J in the alphabet. L can be anywhere from 1 to J minus 1, because I have to leave at least one character to go off to the right. And then, given the choice of production rule, and given the choice of how to split up the string, I need to do two things. I need to match the left part of the string, from I to L, against the first non-terminal in this production rule. And I need to match the right side of this string, starting at index L plus 1 up to J, for the other non-terminal. Okay? Try all production rules. Try all ways of splitting up the string. Once I've picked a rule and a way of splitting up the string, try to recursively match the prefix to the first non-terminal and then try to recursively match the suffix to the second non-terminal. Yes? I'm sorry? Not I is bigger than J. You're right. I'm sorry. I, yes. Thank you. Any other typos? Yeah? Okay.
How many, are you allowed to say A goes to CD, A goes to BC, A goes to SS?
This grammar is in Chomsky normal form. So A goes to A, this is a compact way of writing S goes to AB, or S goes to BC, or S goes to 0, or S goes to 1. Okay? Okay, so we have a recurrence. I think now is a good point for me to stop and say, somebody ask me a question, please. Yes?
I'm trying to find a way to discuss.
Oh, I'm trying all production rules of the form A to BC. I mean, I could make the notation more formal, but would have a bunch of subscripts and stuff in it, and there's enough text on the screen already. So there may be more than one rule. You know, A goes to BC, A goes to YZ, A goes to PQ, A goes to AZ, A goes to AA. Try them all. Yeah.
How do you find L again?
I try them all. L is somewhere between I and J minus 1. I don't know which one it is, so I try them all. I mean, when you see these things in the mathematical notation, what you should be thinking is for loop. Right? This is for L equals I to J minus 1. This is for all production rules A to something something. Yeah.
So L is with I plus 1?
No, L could be I. So remember, I and J are the first and last indices of the substring I'm looking at. So if I want to pass in a string of length 1 to the left, that string of length 1 starts at WI and ends at WI. So L is equal to I in that case. If I want to pass at the other extreme a string of length 1 to the right, that's going to start at J and end at J, in which case L is equal to J minus 1. Yeah. Well, we'll get there. We'll get there. Before we get to the running time, though, we need the next step in our checklist is we need a data structure. How are we going to memorize this function? Now, if you look at what the arguments are, the first argument is an integer between 1 and n. The second argument is an integer between 1 and n. The third argument is some non-terminal in some grammar. But now, how would you actually be given the grammar? Right, the way that you might be given the grammar is literally as a collection of strings that look like this, where each non-terminal gets its own string. And so S is really just the first non-terminal. The letter S doesn't carry any information at all. It's just I've identified it first. I called it S because that's what you called the starting non-terminal. There's no meaning to the letter A here other than it's the second non-terminal. Right? So really, I can think, you know what? I'm going to index all the non-terminals. I'm just going to start numbering them from 1 up to whatever. Okay? And so if I do that numbering, all three of these arguments are just integers from 1 to some higher value. So what data structure allows you to feed in 3 integers and get something back. A 3D array, not a 2D array. And somebody asked me, is it always a 2D array? No, because sometimes you have 3 parameters. Okay? So you're going to memorize this into a 3D array, indexed by I, by J, and by A. Okay, now at this point, trying to draw those arrow diagrams that describe how things are going to depend on each other, my research area is computational geometry. I play with things like cubes all day, every day. I draw pictures like this at least 3 times an hour. I can't do this. So I'm not expecting you to be able to either. So what I'm going to do so we can try to figure out what the dependency order is going to be, is I'm going to just view this 3D array head-on as a 2D array, but keep in mind that every entry in this 2D array is actually itself an array of bits that tell me, okay, what that 2D array is actually storing is for each I and j, tell me which non-terminals match the substring wi through j. All right. When I really implement this, I'm going to implement it as a 3D array, but that's too hard to think about. So I'm going to factor it a little bit, right? And I'm going to have an array, where match ij is which non-terminals A match the string from wi through j. Okay. I could go back and rewrite the recurrence to match this new definition, but in fact, I am not going to. I'm trying to make sure I can actually fit everything on the screen that is important here. Let me try this. Okay, good. All right. So if I'm trying to figure out which non-terminals match substring starting at I and ending at j, I'm going to be making a lot of recursive calls to a lot of different values for those 3 parameters. But one thing to notice is, well, the 3rd parameter just changes wildly. It goes from A and to B, C. I don't know. There's no ordering to these things, so it's just all over the place. But there are 2 possibilities for the first 2 arguments. One is the first stays the same and the second one gets smaller. And the other is the first gets bigger and the second one stays the same. So I'm trying to fill in the spotted ij. I might need, to look in the same row but in earlier columns. Same value of I, smaller value of j. And I might need to look at things in the same column but in later rows. Same value of j, but larger value of I. Okay? So when I'm deep in the bowels of this thing, what I'm actually going to be doing is, well, I don't know which symbols A I need, but I know they're either going to be, the things I need are either going to be directly below, or they're going to be further to the right. Years of practice. Okay. Oh, good. And now I can draw in the back of the cube. Okay, good. All right. Okay, so in order to fill in the gray square there in the middle, I have to look at the array in the correct order so that all the stuff in yellow has already been evaluated. Okay. Now, I'll tell you, you can sort of guess right off the bat, the order that you look at the non-terminals isn't going to matter. The real question is, what order do you consider different i's and different j's? Right? So, in this two-dimensional picture, which is really what you should be focusing on, I need to make sure that I consider the indices I and j in the right order so that when I get to this particular pair ij, I've already considered smaller j's for the same I and larger i's for the same j. So what order should I traverse the array in? Well, I don't want to go down because then the stuff up here gets done before the stuff down there. I'm going to go up. For j, the j arrow is actually right. And does it matter which one of these I have as the inner loop and which one I have of these as the outer loop? No, it doesn't matter. So I want to traverse the array in that order, where you can make the decision, one of these is inner, one of these is outer. Okay, fine. We'll make I the outer loop. Okay. I could also, another answer that would be perfectly reasonable, although it takes a little bit, slightly, a little bit more care to program, is I could go diagonal by diagonal, starting in the lower left and sweeping my way up to the upper right. Now, remember, the answer that you're looking for is actually here. This is, does the string starting in index 1 and ending in index n match some particular non-terminal? And in fact, it's probably the first non-terminal in the array, which means your answer, your final answer is the one that sits here. Right? That's your goal, is the front right top corner of this 3D box. Okay? And the stuff in the back corresponds to shorter substrings, and the stuff closer to the front in this picture, stuff down in this corner is smaller substrings. Stuff up in this corner represents longer substrings. So you're building things up like the sort of generating the strings. You start with small substrings and figure out what they match, and then you build up how larger and larger substrings match, eventually getting to the entire string. Okay. How long does it take to do this? Okay. First of all, let me assume that so n is the length of my input string, and let me write m to be the number of non-terminals, and p to be the number of production rules. Okay. The base case is that those clearly you can just take constant time. I assume there's some reasonable data structure that allows me to tell in constant time, hey, does this non-terminal generate this single symbol? You've got just a lookup table somewhere. So the interesting thing is, how much time do I actually need to spend to evaluate this one spot in the array? Well, first of all, what's the size of this data structure? It's n squared m space. Because I've got n rows, n columns, and m layers, one for each non-terminal. For each of those n squared m things, I need to evaluate something in 2 for loops. For loop, for loop. Yes?
Would it
Well, that's the whole point of memoizing this. I mean, our associative array is that data structure. Because the way that you identify a string that you're passing into the subroutine is start, end. And then you look up in the table for each non-terminal whether that substring matches that non-terminal. Okay? So we don't need any additional things to keep ourselves from repeating, as long as we are careful to evaluate things in the right order. Okay? So the code is going to look like, well, let me just get the picture here. The code is going to be, you know, for I goes from n down to 1. For j goes from, well, in fact, j is always at least I. And then I'm going to consider, you know, all non-terminals in the inner loop. All right? But if I imagine making the decisions in the opposite order, if I say, I don't know where to break things up. So let me just try here for L is all I to j minus 1. And then in the inside loop, I need to consider every non-terminal and every production rule for that non-terminal, which means I'm going to consider all production rules. And then inside that, the you know, 4 levels deep, I'm actually going to make, you know, my 2 recursive calls and update my table. So in the end, I'm using n squared m space, but my running time is n cubed times p. Number of characters in my string cubed, and for every triple of characters, I'm going to look at every production rule. All right. Deliberately, I'm doing this quickly because the thing to remember is it's roughly n cubed time. Usually, again, when you're looking at like some real compiler where the language is fixed in advance, p is a constant, m is a constant. These are things that are hardwired into the code. The only variable in the input is the length of the input string. And so then this third dimension that I've drawn in that cube is only a constant number of bits thick, and so I can just ignore it, think of it as a 2D table. And then the real question is, when I'm filling in this 2D table, what do I have to do? Well, I have to look for each value of R, I have to look at the corresponding substrings and their spots in the table. Sorry, each value of L. So inside the for I and then for J, I have a third for loop for L, and then inside that I look at all the production rules. So I get something that's roughly cubic. For arbitrary grammars, this is essentially the best that we know how to do. Right? There are, in theory, faster algorithms based on the observation that the thing that you're doing here actually structurally resembles matrix multiplication. For I goes this, and it's 3 nested loops over a big table. And there are subcubic time algorithms for matrix multiplication that resemble Karatsuba multiplication for integers. So you can get that down to n to the 2.3179 something, something, something. But you don't. In practice, these faster matrix multiplication algorithms are slower because the matrices aren't the size of the Milky Way galaxy. They're generally only millions by millions. So morally, this is essentially the best you can do for arbitrary grammars. Now, if I came into a compiler researcher's office and said, I've discovered a fantastic new algorithm for parsing C++ programs, it runs in only n squared time. How do you think it would react? It's better than n cubed, right? If he was nice, he would say, that's great. Why don't you go off and compile Linux and come back in a few trillion years, right? You really can't afford anything as big, even as n squared, when you're looking at code bases that are in tens or hundreds of millions of lines long. Any real-world parsing algorithm, if you're parsing anything of even remotely moderate size, has to run in linear time. But I just said this is the best you can do if you have an arbitrary context-free grammar. And so this is the problem when you're designing grammars for things. You have to design the grammar in a way that it supports a faster parsing algorithm. The languages that computational linguists use to model English have faster parsing algorithms. Namely, every human being that speaks English. We don't run an n-cube time algorithm to figure out what a particular English sentence means, unless perhaps you're reading Ulysses. Even then, I have my doubts, but certainly that one, you need something better than a linear time algorithm. The language that we actually use has more additional structure to it. And the evidence that it has more structure is that we can talk faster than that, right? And so computational linguists try to exploit that structure. Programming language designers design their languages in a way that allow faster parsing algorithms than this generic CYK stuff. This algorithm is called CYK after the initials of the 3 people that came up with it. For those parsing algorithms, you will hear about those in 421 if you're a CS major. If you take a natural language processing class, you'll see similar algorithms in that context. If you take 440, you might see this algorithm presented again in a slightly different way. The main point here that I want to raise is sometimes it's not a 2D array. You have to think a little harder. Sometimes it takes more than constant time to fill in one spot in the array. Right? There's an actual for loop required to fill in this spot. Time and space are not synonyms of each other. It isn't just, well, I've got n squared things, so n squared time. And finally, in the end, everything boils down to getting the right recurrence. One last question in the back.
Sorry, I keep throwing out questions.
No, please. That's why we're here.
This three-dimensional array is going to the values that you actually need to compute.
Yes.
So I feel like if we shouldn't just do this, fill it in so that we get all the necessary ones before.
So now you're being clever and you're doing it at exactly the right time. We already have an algorithm that works. And now it's a good time to say, you know what, maybe we don't need all that space. Maybe there's a more efficient way of encoding those bits. Maybe there's a more efficient way, let's look at the grammar and we don't have to consider all these different possibilities. Maybe we can do something a little bit slicker. Lots and lots of stuff you can do. In the worst case, that three-dimensional array might alternate between zeros and ones everywhere. It might just be really horrible and ugly, in which case, no, you're not going to save anything. But in practice, yeah, you're exactly right. In practice, it's going to be sparse. Okay, thank you.